For this problem, we're looking at exactly the same cycloid arch as in the previous problem. So I recopy that down here. Before, we wanted to find the area under this arch. Now we want to find the length of this arch. So how do we do this? Well, here is our theorem that gives arc length here in this section. So basically everything here checks out. We're going to integrate, in this case, from 0 to 2 pi of the square root of x prime of t squared plus y prime of t squared. So what we just need to do right now is to try to simplify what's under that square root. That's our first order of business. So x prime of t is going to be r minus r cosine t. Y prime of t is going to be, derivative of r is 0, and the derivative of minus r cosine t is r sine of t. So when we have x prime of t squared plus y prime of t squared, we end up with r minus r cosine t squared plus r sine t squared. And this is going to be, when we expand everything out, we have an r squared minus 2r squared cosine t plus r squared cosine squared t. And this would be an r squared sine squared t. Okay, so two simplifications we're going to do at this point. Simplification number 1 is every term in here has an r squared in there. So we might as well factor out that r squared. And then cosine squared t plus sine squared t, that's going to be 1. So we'll have 1 plus 1 after factoring out the r squareds. So that's 2 minus 2 cosine t. Okay, so this is our first kind of checkpoint here. We have taken the derivatives of x and y and squared those and added those together. So next step, for this I need a new piece of paper. It's going to be looking at the square root of x prime of t squared plus y prime of t squared. So that is the square root of r squared times 2 minus 2 cosine t. Okay, so one thing here is obvious, that the square root of r squared is going to be just r. It's assumed in this problem r is a positive number times the square root of 2 minus 2 cosine of t. I guess we could also move that 2 outside that square root as a square root 2. But now I want to focus on the most important thing, which is, what do we do with this? It would be nice if we could write this as a perfect square to be able to take the square root. And in fact, there is a way that we can do it by using the following identity, which is that sine squared of t divided by 2 is equal to 1 minus cosine t divided by 2. So here we see what's under the square root is 2 times 1 minus cosine t. So if we multiply this by 4 and this by 4, we end up with 4 sine squared of t over 2 is equal to 2 minus 2 cosine t, which is exactly what is under our square root. So this we can now rewrite as r times the square root of 4 sine squared of t over 2. And so this is going to give us, the square root of 4 is 2r, and the square root of the sine squared of t over 2 is just sine of t over 2. Now, you might wonder, don't we have to put absolute value bars here or something like that? And you're good to wonder and worry about this, but t is running from 0 to 2 pi, which means that t over 2 is running from 0 to pi, and on this interval, sine of t over 2 is always non-negative, so we don't have to worry about absolute value bars or anything like that. So at this point, all we have to do is say, well, we've got the integral from 0 to 2 pi of 2r sine of t over 2 dt, because we just took this square root of x prime of t squared plus y prime of t squared, and we spent all of from here to here crunching it out, simplifying it, getting rid of the square root. Okay, so our very last thing that we have to do, is actually evaluate this integral. I think a little substitution here of u is t over 2, du is 1/2 dt, so that would make 2 du equal to dt. So the integral of 2, so dt is becoming 2 du, so we have 4r sine of u du. When t is 0, u is 0. When t is 2 pi, u is pi. So we are left with, I think I can squeeze this end down here, minus 4r cosine of u, and plug in 0 to pi. And so this should give us 8r. Okay, so a lot going on there. Manipulating the square root to see that this was a perfect square in the square root, that was tricky, especially because you have to recall this trig identity here. And of course, we are using this arc length formula.